the Laplace equation is the most fundamental equation basically that I know, period. It's not only because it has relations with multiple physics, even on problems that they are mathematical in nature with no physics involved, the Laplace equation comes to play a significant role, okay? So there's no way you can avoid having to do something with the Laplace equation in any course you take, unless your professor doesn't like mathematics. So if you don't hear anything about the Laplace equation, ask him, do you know what the Laplace equation is? Okay? It's very essential. So what I'm going to do is I'm going to jump a few slides, go directly to the real problem. So the Laplace equation looks like second derivative of u plus second derivative of y equal to 0. So I'm writing it now in 2 dimensions because really in 1 dimension doesn't make a lot of sense. So this looks like actually the steady state diffusion equation, heat conduction equation in 2 dimensions. And so I'm taking some boundary conditions that are what I call essential boundary conditions. I specify the u on the boundary. Let me see if there is a plot. So I put a u equal to 0 on the bottom, on the top, on the left. And then obviously I cannot put 0 on the right because then the answer is going to be 0. So I have to put some given function f of y on one side. All right, so we can at least get something of interest. Okay, so that's the problem we need to solve. That's the Laplace equation in 2 dimensions. And obviously, we're going to do separation of variables. So we're going to assume that there is a solution that is x of little x, y of little y. So we're going to plug it in, do the regular things, separate capital X and capital Y variables. Obviously, these 2 things have to be the same. I call this a constant lambda. And I get 2 wonderful ordinary differential equations, but by now, you should know how to solve them, okay? So now, before we solve these equations, obviously, we're going to have to put some boundary conditions in these ordinary differential equations. And the boundary conditions come from the picture I had before. So I'm going to go directly on the image. Can you actually guess what the boundary conditions will be? So remember that the solution is capital of X times capital of Y. So what type of boundary condition this condition will give me? Or that condition, pick up anything. How about this condition, the easy one? Right? How about this condition? Will this work for you? Look at them carefully on the bottom and tell me if you're happy with them. So I see on the left, u is equal to 0. So at x equal to 0, this equal to 0. So obviously, you're not going to take the whole y function to be equal to 0. So x at 0 will be equal to 0. Similarly, this, for all x's at the bottom and the top has to be equal to 0. Obviously, you're not going to take the whole x to be 0. So y at 0 and y at b equal to 0. We agree? I mean, that's sort of common sense, so we don't get the 0 solution. Now, the only boundary where we have not said anything yet, and you can guess how this is going to come, is the boundary condition at x equal to a. So we're going to deal with this. But for now, I can easily see I had a second order differential equation, ODE for y, and I have 2 boundary conditions at the 2 ends. So I have a 2-point boundary value problem. So I can solve it. And if I can solve it, isn't this the solution that we have seen from the first lecture on PDEs? Do we agree that these are the eigenvalues and these are the eigenfunctions for capital Y? Yep. Okay, I heard a very weak yeah. Just to confirm for those listening, a very weak yeah. Okay, so that's the solution for capital of Y. Okay, so now we have to solve this equation. And this equation obviously has solutions that are exponentials in little x. And for no particular reason, but just mathematical convenience, instead of using the exponentials e to the lambda x, I'm going to use hyperbolic sign and cosine. You don't have a problem with that, right? It's the same, just another set of independent basis functions. Now, remember that what was the boundary condition for capital X that we had identified? That at 0 is equal to 0. So at 0, the hyperbolic sign is 0. So K1 has to be equal to 0. Okay? So basically, the capital X that we identify is some constant times this hyperbolic sign of the square root of lambda, which is n pi over b. And so let's put all this together. And obviously, we're going to have to use a combination. We have to use, actually, I have to be sure that I jump. OK, this slide is good. So we're going to have to use a combination of the eigenfunctions we identified. So these are the eigenfunctions in x, in y. So we're going to take a linear combination with some coefficient Cn. And this will be sort of a standard way that will allow us to compute the boundary condition, on x equal to b. Okay? So that's what I'm going to do next. I'm sorry, for x equal to a. Okay? So for x equal to a, the boundary condition was u equal to f of y. Can you see now if you put here x equal to a, that this needs to give you f of y, how you're going to compute Cn? Can you look at this equation and tell me what the idea here is? So at x equal to a, right, this should be f of y. And then we're going to have summation of Cn times this x there is going to become a. And then I have this hyperbolic sign of n pi y over b. So can you tell me how I can compute from f of y the coefficient Cn? This requires an answer that cannot be a yes. Say it again. Apply orthogonality or directly using the Fourier equation, right? Because, for example, you can see, so this will be fixed, right? X will be equal to a. You can see that Cn times this hyperbolic sign evaluated at a are nothing else but the Fourier coefficients in a sign expansion of f of y, correct? Okay, so, and obviously we don't have sines and cosines here, we only have a sign expansion. So here's the answer. Come on, where is my answer? So Cn times this hyperbolic sign, that the whole thing will be the Fourier coefficient, equal 2 over b, integral from 0 to b of this, effectively using orthogonality, as you said. And by the way, why there is a 2 there, why I have a 2, I remember the Euler's equation don't have a 2 there. Why there is a 2 there? Why there is a 2? Well, this is a sign expansion, so why there is a 2 here? I mean, you can see the integration, right, is not from minus b to b, is from 0 to b. So what does that imply? We have taken an extension of this function. What type of extension? What type of extension we took for f to get the sign expansion? Can you see that originally this integral is supposed to be 1 over b times integral of minus b to b, right? So when you go home, think that this integral became 2 over b, integral from 0 to b, which is nice because f of y originally is only defined from 0 to b, okay? So you go home and you think about that. And that's the answer. And there is no aha, because if I trivialize everything, then we are going down the drain overnight, okay? And I have to cover about 50 slides today. Reality. When reality hits you, you react. Okay? So So that's the problem, and the solution looks like this. So that's the summary, and someone actually, out of curiosity, can say, you know, this Fourier expansion, I don't see anything like 1 over n squared in the coefficient, something nice that tells me that this thing converges. So obviously, you know, nice to have an expansion, but does it actually work? You know, if I take 3 terms or 4 terms, does it converge? And you can see that it is not clear, basically. Okay? So now notice that there is a hyperbolic sign here, all right? And there is a hyperbolic sign over there. So when n is very large, what's a good approximation for the hyperbolic sign is e to the x minus e to the minus x over 2. So when x is very big, what's a good approximation of the hyperbolic sign? When x is very big. E to the x plus minus e to the minus x over 2. So what happens when x goes to infinity? So it's e to the x over 2, right? So if I approximate this hyperbolic sign as e of that argument, okay, and forget the 2's because they will cancel, and this thing in the denominator is e to the npa over b, effectively you will get something that that looks like the ratio there will be e to the minus n pi a minus x over b. So so for large n, all right, for large n, there is the hope that this thing will actually decay exponentially fast, okay? And all of this assuming that a minus x is not very small, okay? So the larger a minus x is, the faster this thing will converge to 0. So that's the reason, basically, why the series converges. It is not apparent, as we have seen before, having 1 over n or 1 over n squared or something like that. Okay, let me, there's one little example that there's nothing there. So if the function f of y looks like this triangular, right, from 0 to 2, and x is from 0 to 3, so that's my domain, you can do all the calculations and evaluate u of x of t, and the solution looks like, you know, this looks like a steady state heat conduction, right? So it's like putting a function, the triangular function, on this boundary. So the steady state temperature, the contours will look like what you see on the left, and on the right you have a 3D version, of this. Okay, now solving the Laplace equation on a disk. That's an extremely fundamental problem, and if you want to impress me, when you do your homework, do some search on the web, on Wikipedia, in books, and say Laplace equation on a disk, because people still write articles about it, okay? And there are fancy approximations, fancy equations that will always impress us because it's all about the Laplace equation. So how do we solve, if we have to solve, let's say, a steady state heat conduction problem, which is the Laplace equation, and we assume that we have essential boundary conditions. So I give you the temperature on the boundary. So we know the temperature is a function of theta. We would like to solve this, and obviously because the boundary conditions in terms of theta, the correct coordinates to express the Laplace equation and solve it is polar coordinates. And I am not going to tell you what polar coordinates are. I am assuming you guys know, all right? And I'm assuming you can take the Laplace equation, substitute x equal r cosine of theta and y equal r sine of theta, do chain rule, change the derivatives, and after some exercise, this is the governing, this is the equation in polar coordinates of the Laplace equation, okay? It is as important as the Laplace equation in the x and y coordinates. So this is what we want to solve. We want to solve this Laplace equation, okay, in a disk. And so we know that at r equal to a, the solution is f of theta. So effectively, we need to identify the eigenvalues and eigenvectors for the Laplace equation in polar coordinates. By the way, you cannot go and use the eigenfunctions in Cartesian coordinates and then say, okay, put x equal r cosine theta, r sine theta, here they are. It doesn't work like that, okay? So you're going to have to recompute them for this differential equation. Okay, so, and actually it's fun to compute them because you get interesting things, okay? So the only thing we're going to assume is that the solution is periodic in the angle theta with a period 2 pi, right? And we're going to constrain, basically, that the solution doesn't explode inside the domain, so it's finite. It's bounded, okay? So we're going to use, again, separation of variables, capital R of little r, capital theta of little theta. We're going to plug it in, and we're going to separate variables. And it does work, actually, as I can see. Here is everything's a function of little r, here is a function of little theta, and this is equal to a constant, and I get 2 ordinary differential equations. That's why we actually study second-order differential equations. Does the first equation remind you anything? What does it remind you? What equation is that? Does it come with a name? The other day I was doing, a puzzle at home, and he was saying a famous Swiss mathematician. All right, there are so many. So who was that famous Swiss mathematician that I had to write with 5 letters? Yes, who? Who was that? Come on, what equation is that? We did this before. Say it again. Ah, what did you say? Euler. All right. So you will have failed in the puzzle, because that's what he was asking. All right, the famous Swiss mathematician, and he was Euler. Okay? So that's the Euler equation. And you remember what solutions it admits? What type of solutions we have for the Euler? So before we did these power series solutions for second-order ODEs, like, we did the Bessel function, not the Bessel functions, what was it? What functions did we do? We did some more interesting functions, okay? But the Euler equation had some very simple solutions of what form? So when, what form was the solutions to the Euler equation? What does it say on the slides? Or on the next slide, or on the next slide. So what are the solutions to the Euler equation? It's Friday. What's the solutions to the Euler equation? You're not sure. Say it again. Not quite. Well, I mean, that can happen. Actually, you can get some log if it happens that the 2 solutions are the same. So in the most basic form, 2 different roots of the characteristic equation, what is the solution to the Euler equation? Come on, guys. K1 what? R to the mu. So it's R to some power. It's R to some power, okay? So that's the solution to the Euler equations. And you have to solve the characteristic equation here, which, if you plug in R to some power, let's say alpha, you are going to get here alpha times alpha minus 1 plus alpha minus lambda, all right? So the alpha will cancel, you get alpha squared equal to lambda, so you will get plus minus square root of lambda in the powers, right? Okay, so, and obviously this equation, what type of solutions it has? Of course, it depends what lambda is, so we will see if lambda is positive or negative. So in those cases, like, I mean, even maybe I omitted this in some of the examples, but you don't know if lambda is going to be a real number, an imaginary number, if it's real, if it's positive, negative, 0. So you actually have to try all of these things. So the thing we are not going to play with we're going to take lambda to be real, and you can actually solve that that's the case. But lambda can be negative, can be 0, can be positive. And I can tell you, if you forget, for example, to investigate the case lambda equal to 0, you will do a huge mistake, because lambda equals 0, it will give us an eigenfunction that is not 0. If it was giving 0, then we say, who cares? But it will give an eigenfunction that is not 0. So if we take lambda to be negative, so we can set lambda equal minus mu squared with mu positive. So the equation for theta is going to look like this. Which way you can make this to be a periodic in the angle theta? There is no way exponentials to be periodic, so C1 and C2 has to be 0. So this gives me the 0 solution. And so basically, forget about it. Basically, we cannot have lambda less than 0. If lambda equal to 0, all right, if that term there was plus lambda capital theta, if lambda 0, then I get this equal to 0. So theta is a linear function. The only way for this to be periodic is C2 to be 0. So the angle theta is constant. I mean, the function capital theta is constant. And if you take lambda to be 0, the equation we had for capital R will give me this. And this has a solution K1 plus K2 log of R. And log of R is not good. Why log of R is not good? Because we made the assumption that we're looking for solutions that they are fine, that they're bounded for inside the disk. So at R equals 0, log of 0 blows up. So we don't want that. So we want constant. So theta, capital theta is constant, capital R is constant. So effectively, lambda equal to 0 has an eigenfunction which is equal to constant, and so 1, right? We don't really care about the constant. So remember, lambda equal to 0 gives an eigenfunction that is equal to 1. So when we take a linear combination of all possible eigenfunctions, you cannot omit this case lambda equal to 0, because then basically you have half-baked goods. You may get your nice sines and cosines. You omit this, you will never get the right solution. All right. So then we have the case lambda greater than 0. So if lambda is greater than 0, the equation for capital theta obviously will give you sines and cosines. So obviously I can see my eigenfunctions being sines and cosines here. For this to be periodic in the angle theta, what is the constraint on mu? I need my capital theta to be periodic with period 2 pi. So what is the constraint I need to have on little mu? The little mu needs to be how are you going to make sine? I mean, if this was sine of square root of 3 times theta, is that periodic with period 2 pi? So what do I need to say about mu? It has to be an integer, right? So mu has to be equal to n. So this is my, my eigenvalues would be then n squared, all right? But this defines my eigenvalues, okay? And if you then look at the corresponding equation for capital R, we said that's the Euler equation. You get r to the mu and r to the minus mu. The coefficient mu comes because you remember, if you put a general solution r to some power alpha and you solve, you will see that alpha has to be either mu or minus mu. So these are the two independent solutions of the Euler equation that you forgot about it. And we don't want this to blow up. So what term do we keep if we don't want this to blow up at r equal to 0? We don't want this to blow up at r equal to 0. So we'll take k2 equal to 0. We'll only keep that. And that's the final answer. Come on, where is my final answer? My final answer is that for the case lambda greater than 0, we have eigenfunctions that they're of the form r to the n cosine of n theta and r to the n sine of n theta. Where do they come? This is my r, right? And that's my sine and cosine. So if I take them separately, I get two sets of eigenfunctions, r to the n cosine of theta and r to the n sine of theta. And then the question is, I need to form a linear combination of those, right? And look my linear combination and tell me where is this term coming from. So I took now a linear combination of all the bases, all the eigenfunctions. Where did this constant came on the front? Lambda equal to 0, right? So if you forget it, it's like forgetting the mean of the response, you know, everything will be completely messed up. And I have to tell you, in lots of problems, so by the way, this looks like a Fourier expansion. We will come to it, right? It's a Fourier expansion, but we got it not as a Fourier expansion. We got this by taking linear combinations of the fundamental solutions to our problem, right? So we combine them, and there is this whole thing looks like a Fourier expansion. It is actually a Fourier expansion, which means can we actually get easily these coefficients C0, Cn, and Kn? How do we get those coefficients? There is something we have not applied yet in solving this problem. What boundary condition we have not applied yet? Remember, we said it's finite, it's not, it doesn't explode, it's periodic, we apply that. But did we apply the boundary condition that on the boundary, the solution is f of theta? Don't remember that, okay? So now we have to apply that at r equal to the radius, whatever that was. There it is. The solution has to be f of theta. So basically, f of theta has to be equal to that. And immediately you can identify what the coefficients C0, Cn, and Kn have to be by using the Euler formula, a very famous Swiss mathematician, okay? An Euler formula. All right, and that's the answers, and we are done. Now, again, I have to tell you, if you search on the web, you're going to find books, papers, everything, and sometimes the expansion will not involve cosines and sines. So what I ask you in the homework, which is actually the first part of the homework is trivial. The second part, I wanted you to see if you can actually go and see what is out there. Because even though the solution, you will get it in one line, there is a simplification that somehow you will only identify it and find it if you do a little bit of searching. Okay? And if you find it or not, it's okay. I just want to be happy, so I want you to find it, okay? So it's not okay. So I would be happy if somebody identifies what the easy solution is. Okay, so we finished with the Laplace equation, and it's 10:59, which is not enough time, but enough time to move forward. So we're gonna talk about the wave equation, okay? Now, doing the wave equation in 20 minutes, it's a miracle of nature, but we can try, okay? So we're going to do elastic waves on a little rope or a rod. So we're going to have this string, if you like, that we fix it at x equal to 0 and x equal to L. And at each location x, and at each time t, u is going to be the lateral displacement on the plane, basically. So we're going to do plane waves, all right? Actually, we're going to do one-dimensional waves, but the deformation is lateral. It's going to be in the y-axis, and we're going to call it u of x and t. I am not going to derive anything. It's in the notes, sort of in an appendix. This is the wave equation, a squared u of xx equal u dt. You notice, in difference from the diffusion equation, there is a second derivative in time now, right? This is the fundamentals of the wave equation. This looks like what we had before, the alpha squared being like a diffusivity, but actually, literally here, a is the wave speed, okay? And there is a nice formula that connects the wave speed with the tension of the string and the density of the material of the string that you use here. But for us is a squared uxx equal utt, and again, a is really the wave speed, assuming that this equation is going to give us waves. So we're going to take the same boundary conditions, u at x equals 0 equals 0, u at L equals 0, and notice there is second derivatives with respect to time, so we're going to need two initial conditions, and one of them is going to be, we're going to prescribe the initial displacement, and the other one, we're going to prescribe the velocity. So here, we prescribe the velocity initially to 0, and the displacement equal to f of x. I mean, something has to be non-zero, right? So this is the easiest problem. We'll take the initial displacement not to be 0, and put everything else equal to 0, okay? So we need to solve this nice equation, and we need to sort of figure out why do we call this the wave equation, and where are the waves, all right? Everybody likes waves, okay? So we need to see where the waves are. So separation of variables, nothing fancy, keep doing what we always do. We get two ODEs, one for capital X, one for capital T. The only difference from before is that the equation now for capital T, this is the equation in time, it's a second order ordinary differential equation. So we have one ODE for X, right, and one ODE with an independent variable being time, okay? So obviously, our job will be to apply first some boundary conditions on capital X and capital T, and then somehow identify some eigenvalues and eigenfunctions, take a combination, and then eventually impose the one of the initial conditions. You remember the non-zero initial velocity, and then we're done. Okay. So when it comes to the, applying the obvious boundary conditions, which is this 0 condition and that condition, you're not going to have any argument that capital X at 0 and capital X at L is 0, right? You remember our solution is capital X times capital of T, so that would be the obvious thing. So effectively, we're going to have two conditions on capital X, so we're done. Basically, we can solve for capital X. And then, oh, I'm sorry. I thought the non-zero, I mentioned before, we have to satisfy the non-zero velocity. It's actually the initial velocity is 0. So when we finish this, we're going to have to satisfy the initial displacement of the string that is equal to f of x, okay? All right, so we need to take care of that 0 velocity for capital T. And so actually before, I'm following the slides in sequence. So the ordinary differential equation for capital X, it's identical to what we have done up to now, right? That's our standard second order two-point boundary value problem. So there are the eigenfunctions, and there are the eigenvalues, okay? We agree? There's nothing fancy there, right? We have this whole thing, 0 at the end, okay? So from applying the boundary condition at x equal to L, we get these eigenvalues. So these are the eigenfunctions. And then we have to solve this equation, okay? So if you solve this equation for these lambdas, and by the way, you notice a nice thing having an alpha square, and this being a square, the squares combine together. So you can get a solution that involves cosines and sines. And I remind you, our initial, the derivative of capital T with respect to time t at time t equal to 0 has to be equal to 0. You remember, we prescribed the initial displacement being some function, and then we said the initial velocity has to be equal to 0. So the initial velocity will be the derivative of this with respect to t. If you take derivatives with respect to t, This will become a cosine, which at time 0 is 1. And this will become a sine. So which of the two terms will be 0? The initial velocity has to be 0 at t equal to 0. Which term should I put 0? Which one? Which one? K2, right? Because if you take derivatives, this will become K2 cosine. This will become a sine, which at time 0 is 0. So this whole thing, K2 cosine, has to become equal to 0. So K2 equal to 0. So basically, my eigenfunctions coming from capital T is cosine of n pi a t over L. So I can combine this with that. And if you combine them, you get basically these nice eigenfunctions for x and t. So you have sines n pi x over L for the in x, and cosine n pi a t over L. And again, the reason we got cosines and not sines is because we had an initial condition for the derivative, right, for the velocity. So that gave us a cosine. OK? And what is left is to actually compute the coefficients in, so when we take a linear combination of these eigenfunctions, exactly as we have done in all the cases, now we have to identify Cn. We know that u at x, any x and time 0 is my function f of x. So can you identify the coefficients Cn from f of x? What formula are you going to use? And at time 0, this becomes cosine of 0 is 1. So can you identify Cn directly? What formula are you going to use? Say it again. My 5 letters puzzle. The Euler formula, all right? So if you use the Euler formula, there is the answer, okay? And again, notice I'm putting a 2 there, so I'm integrating from 0 to L. All right, so that's the solution. We're done, okay? So a little bit of discussion on what this solution means, okay? And where are the waves, by the way? I mean, you can actually see in principle that you can concentrate on a given x, and you can see that this is a periodic motion for every x defined by this cosine. But also you can concentrate for a given t and see that somehow there is some periodicity in the modes of oscillation that you get, okay, defined by this sine of n pi x over L. So let me just go to the next slide. So the period in time is defined as 2L over NA for a given n. Can everybody see this? I mean, plug in here t equal 2L over NA. What do you get? You get the 2 pi, okay? So, I mean, that's the periodicity of the cosine. So the period is 2L over NA. Remember this nice formula, okay? And the corresponding frequency, the angular frequency, 2 pi over t, is n pi a over L. All right, so these are the natural frequencies of the string. So again, the periods in time are defined by looking on the cosine. Right, so if you take t to be t plus 2L over NA, you're going to get basically back from where you started, because you're going to get the 2 pi term there. Okay. Now, if you look now on the first term, right, so if you fix the time and you look at the displacement of the string for all x's, you're going to get sine n pi x over L. And a sine also has a period in x. How should we call that period of something? How do you call, when something is periodic in space, how do you call that? You know, so period, you know, usually refers to time. So how should we call the period in space? but the period, how should we call the period in X? What names go with that? Say it again? No, that was, I heard it. The wavelength, okay? So, so the wavelength defined by sine n pi x over L, it's actually 2L over L, okay? So again, we have a frequency and a period in time. We have a period and a frequency, well, period, that's the only thing I'm going to use, which is the wavelength in space, which is 2L over N. And here are some of the modes that you get, right? So if I plot the modes for this string, I updated actually this thing just for your convenience this morning. So I put so we said that the angular frequencies are n pi a over L. So for n equal to 1, you get this, n equal 2, n equal 3 equal that. And the wavelengths are 2L over N. So here is 2L, L, and 2L over 3. And you can actually see the wavelength, right? So this goes to 0, so it will take another L to go back to where it started. You see that? Right? So the wavelength for this mode is 2L. The wavelength in this mode is L. And the wavelength for this mode is 2L over 3. And of course, this continues for all n's. But those are the three principal modes of vibrations, basically, that you get for this string. Okay. So let me, I'm going to do an example, and it's very similar to what I asked you to do in the homework. And if one of you wants to impress me, not like that you care, you can actually submit a nice script where you have a nice movie that shows how the whole beam that I gave you vibrates with time, right? That would be nice. Something nice, okay? So you can, once you compute the solution, just plot it, but plot it as a movie. Okay, that's your homework for this weekend. So we take the initial displacement to be f of x. The initial velocity, again, is equal to 0. So if you solve it, you know, you do exactly, you find with the Euler formula the coefficients. This is the expansion. This is the coefficients. Just pure algebra. And what I'm interested in is actually to give you how the solution looks like, okay? That has sort of, you will really need to study this for a few hours to get a good sense of what is going on. But you can see at time t equal to 0, okay? This is my initial displacement, right? That triangular is what I gave you. But look at time t equal 4. It's a little bit unchanged for x, let's say, up to location 2. Then it moves to this line, and it's unchanged for the rest going all the way to 30. And then you can see at time t equal 15, the displacement has become negative. It looks like that, all right? And actually, t equal 15 for this problem is half the period, which means now the motion is going to be reversed, and it's going to go back to where it started at time t equal to 0 in another 15 seconds. And if you really want to plot it, you see something amazing. So if you plot the solution ux of t at different locations x for the period is 30. So actually, when you plot it, you can immediately see that the period of motion is equal to 30 here. But observe what is interesting. What's going on here? So I am plotting this, right? I'm plotting at a given x, the motion, how ux of t looks for a given x. So when you look, let's say, at x equal 5, what is going on there? Can you tell me on that? So what's going on? I mean, if this solution is correct, what is going on at x equal 5 for about a third of the period? I mean, if this plot is correct, what is going on at x equal 5? Let's say for this little period there, I cannot zoom it now, right? And also up there, you can see. So what's going on? Nothing. All right? So that's a very interesting thing. So, so there is no motion in part of the string for about 1/3 of the period. okay? So that's why I said if you actually make a movie, you will look at it and you will say, wow, how come I did not understand this thing? That this is what you actually get, okay? You get actually nothing. So it's 11:16, and I'm doing fantastically well for a Friday. And slide 144, all right? So let me go, because there is a homework also due that is sort of a little bit of trivial thing. Let me just say with words, because it was on an earlier slide that I omitted. If you look at the wave equation, and you tried sort of to compute second derivatives with respect to space and with respect to time, so you can see, actually, you can convince yourselves that the differential equation is satisfied. You realize there is a problem that the second order derivatives, the series that you have, doesn't seem to actually be a convergent series. So even though we got a solution that does the job, it seems we cannot differentiate twice. And somebody can argue, is it really the solution? Well, it is. It's just the second derivative doesn't exist the way we compute it without power series expansion, okay? So if you want to solve this problem, there is a very nice way to solve it, and I'm going to give you in the remaining 3 minutes what the answer is going to be, all right? So you can write, actually, the solution to the wave equation as 1/2 of hx minus at plus hx plus at, where h is a node periodic extension of the initial displacement f of x. And I remind you what is a node periodic extension of f. So the solution to the wave equation can be written as that, okay, where h is a node periodic extension of f. And obviously, if this is correct, and you put the correct assumptions on regularity or on f, so for example, that f is continuous second order differentiable, then the same will be true with some boundary conditions on f and its derivatives. The same will be true for h. And if h has second derivatives continuously, then u has second derivatives, and then the differential equation satisfied, nothing to worry about it, okay? So this will actually be sort of a more elegant way to get a solution to the wave equation. But look at it, right? It is not obvious. I'm just telling you the solution to the wave equation is 1/2 of h at x minus at and x plus at, where so you have changed variables, and h of x is a node periodic extension of f. The proof of this, actually, and that's not what I want you to do in the homework, the proof of this is rather trivial, because if you remember, we have a node periodic extension of f, so h will be a sign expansion, all right? So the coefficients are given by this, okay? So from this h of x, all right, this is the Fourier expansion of f of x using a node periodic extension of f. So you can actually compute the sign of x minus at and x plus at from this Fourier expansion. And then if you add the cosine terms here, this second terms plus and minus will cancel. And when you take the average, you actually see immediately that the average of those two is this, which we have shown be the Fourier expansion we got with the previous method. So effectively, the two solutions are the same. There's nothing different, but this expansion, the way we had it, you cannot actually differentiate. You cannot take second derivatives and all of these things. But this, yes, you can if f is differentiable. So again, you have things that look the same, but the way you treat derivatives, obviously, is not the same. Okay? And let me see if I need to jump. And I'm going to give you rapidly what the conditions are. Basically, extremely mild conditions, right? So you need to be able to take derivatives, two derivatives of this, to apply them to the differential equation. So h has to have two derivatives. So f prime and f double prime need to be continuous on the interval 0, 12. And also there is an extra condition that I'm going to throw it at U, and you can think about it because we mentioned this when we discuss odd periodic extensions of functions, that because H double prime is an odd extension of F double prime at 0 has to be 0, and F double prime at L has to be 0. All right? You can go back and look at the slides on odd periodic extensions of functions, and you will see, because you remember at points of discontinuity, the expansion converges on the average. That average, because it's an odd periodic expansion, has to be 0. Okay? So basically, you have to satisfy this equal to 0 and this equal to 0. But if you have a displacement of the string that is a smooth one, differentiable with these boundary conditions, then U is twice differentiable, and actually you can plug it in the equation, and everything is taken care of. Now, let me just say, if it happens that, let's say, these conditions are not satisfied, this equation on the top is still a nice solution to the wave equation, but it will have some singularities. So at some points, maybe the solution is not quite right, okay? But, you know, for engineers, it will still be a right solution. And I don't think there is a slide 155. Actually, let me just put it on 155 because this is extremely important. So let me just say with words, in diffusion problems, if you have any discontinuity in the initial or boundary conditions, it dies out with time. That's what diffusion means. Diffusion smooths things out. Like, you know what? Put whatever temperature or fluxes you want in this room. At the end of the day, the temperature here will be the average of the temperature around. However, with the wave equation, if you have any discontinuities in the boundary conditions or initial conditions, those discontinuities will persist forever. Huge difference between the wave. Diffusion smooths things out. Wave does not forget, and it does not forgive. Okay? And with that said, have a good weekend. I'll see you with another sort of topic to figure out what it is on Monday.